Hey there again. We're going to talk about enthalpy today. So we can burn a match, we can light it on fire, and it releases its heat to the surroundings. And we want to figure out how much heat is that exothermic reaction. So we're going to learn how to do heat flow calculations in this section. So we're going to talk about calorimetry. So what is calorimetry? Calorimetry is the precise measurement of heat flow, either going in or coming out of a physical or chemical process. So you can have phase changes in calorimetry, or you can have a chemical reaction. And we use special machinery called a calorimeter to do this measurement. I used to work at Dow Chemical, and I worked with a chemist, and all she did was take calorimetry readings to make sure of the heat changes, energy changes in a system, because we wanted to make sure we had correct big giant tanks to do these chemical reactions in, and we didn't want the tanks to blow up or implode or anything like that because of the heat changes. So heat is very, very important. We're going to talk about heat releasing or absorbing in this reaction. So we're going to look at the heat of the system. That's what this says. And we can also use the symbol delta H, which is a heat change. So any heat that is released by surroundings is going to be the opposite charge, opposite sign of the system. So these are going to be equal and opposite signs. Okay, and we're going to use this formula, mass times specific heat times delta T, to figure out that change. Okay, so remember, this is change in temperature, this is specific heat, and this is mass in grams. Is going to give us a Q number, either in calories or joules. And we can also call that delta H. So we, in lab, we can make an easy one just taking two styrofoam cups and nesting them together. It holds onto the heat pretty well. We throw a thermometer in there. We have a little stirrer in there so that we can keep the stuff mixing around. And we do these usually in water. And we see the temperature change. So we're looking for a temperature change. So this is a really simple calorimeter. So we're looking for calories, so that's why it's called calorimeter. If we have something at constant pressure, which is what we would have in the lab, we are going to look at for the enthalpy, the H of the system. So that's the heat content of that system. It's called enthalpy. So here's a fancier one, and so this is the kind she used. She had electrical leads here. She had oxygen intake valve. She had a firing element. So it's like a little sparker, like in a big lighter, a little sparker. And then she would have oxygen at high temperature. She would burn that sample and then see how much heat it made by looking at the temperature change. So they use these kind of things for checking the calories on products that you have, that you eat. Oh, and the fancy name for that is a bomb calorimeter, because this is all metal, so you're keeping this whole system at a constant volume. So this is a bomb calorimeter. Doesn't mean it explodes. It's just a really thick-walled steel container. So let's see if we can figure out the enthalpy change when we have water with this acid added to water with that much base. So this is an acid-base reaction, and we're going to see how much heat is generated with that reaction. And we have a temperature change from 25 to 32, and we know everything is 1 gram per milliliter for density. So here's the specific heat for water. We added 25 mils of the acid, 25 mils of the base, so we have a total volume of 50 milliliters, which is the same thing as 50 grams because of that density. We have a temperature change of starting at 25 going to 32. We always go 32 minus 25 to get us that delta T. Okay? And we're going to use the formula. Delta H is the Q, the heat number, joules, of the mass times specific heat times the temperature. So let's see if we can do this math. We're going to look for delta H. So we figured out the mass is 50 milliliters times the density is 50 grams for that 2 sets of water that we put together. The acid and the base makes 50 grams. We do final minus initial. This is important. Always take the ending number minus the beginning number. 32 minus 25 gives you 7. Then we throw this all into the equation for delta H. Negative mass, so 50 grams here. C for water is 4.18. And then change in temperature 7. And so we have a negative sign here. So we're going to have that all multiplied together. Try that in your calculator. Let's look at sig figs for the given here. This is not a given, it's a constant, so don't use that for your sig figs. Well, we have 3 there, and we have 3 there. So we're going to have 3 in our answer. And so I would say, let's go back and double check this. I think because they had 2 here, they rounded 2, but I would recommend, oh, I see. Because remember the adding and subtracting rule, you can only have the number of sig figs in this decimal place. So we have 7 is our final answer here. So yes, we need to have 2 sig figs in our answer because we have 2 there, and that's from the adding and subtracting rule. We have to round to that place right there. So this number right here is 2 sig figs. It's in this formula, so I have to round to 2 sig figs. So they are correct. So I look at 1, 2, look at the 6, it makes that 4 go up to a 5. I have negative 1.5 times 10 to the 3 joules, or I could have said 1500 joules, or negative 1.5 kilojoules. This is negative because we had an exothermic reaction. We had the temperature go up. Okay, so we have a negative answer. Sign is negative, the reaction releases that many kilojoules because the heat's released. The heat released by the system equals the heat absorbed by the surroundings. About 4 joules of heat raises the temperature, so we're just making sure this makes sense. So this was exothermic reaction. It gave off heat to the surroundings, so it's exothermic. You can try this one yourself, see if you could do this one all by yourself. And let's talk about thermochemical equations. How can you express the enthalpy change in a chemical equation? This is what we do. We add it to the actual chemical equation, the reaction. It's either in the reactant or the product side. So this reaction is a thermochemical reaction. We have these two reactants, and we have a product, and we also have heat generated, so it's exothermic, and we're releasing this much kilojoules of energy when this happens. We have to make sure we are using the right states of matter. This is a solid and a liquid water, making this solid precipitate. So always double check your states when you grab these when you grab the numbers off of a chart, that you have the right states of matter, the right phases of matter. So you can write it like this. This is saying that there's energy on this side. When we're done with the reaction, we see energy. Or you can write it like this. So negative signs for delta H means you have an exothermic reaction. You can write it this way, or you can write it that way. They both mean the same thing. So this is saying that when I put these up here, they had a lot of energy in them. And when I did the reaction, this product has less energy, so it's lower down on this energy chart, and we release that much kilojoules of energy when this happened. So here's the endothermic reaction. We start with something that's really low energy. Oops, sorry. We add energy to this system, and we get the products here. So this is an endothermic, trying to show you that we started low energy, and these products have more energy in them afterwards when we added 129 kilojoules. So let's see if we can use this in a real reaction. We're going to calculate the amount of heat in kilojoules when we decompose this thing. So do you remember what type of reaction this is? We're starting with this on the left side. We're going to form products. So this is a decomposition reaction. We have to figure out the balanced equation first. So here's the reaction. We have this on the left side, and we're making these products. So This is a decomposition reaction. It's saying that it takes 129 kilojoules for every 2 moles of this. So we have to put energy on this side. So if you see energy on this side, it's endothermic. If you see it written not here but over here, it's going to have a plus sign. So we're going to try to figure out how many kilojoules to decompose 2 moles of this. We're going to use this conversion factor. There's 129 kilojoules used for 2 moles to decompose this. And we want to know the delta H. They gave us this many moles to start with. Okay, so this is the balanced equation, but we in actuality have this many moles, so we have to figure out how many moles of energy would be for that. So we know there's 129 for 2 moles. So how many for this many moles? You can use that conversion factor there and figure out the 144. So let's see about sig figs here. We had 3 sig figs given. This is a constant, so we don't use that for sig figs. We only get what we were given in the original problem. So we're going to have 3 sig figs. 3 sig figs are our answer. So here's one for you to try. We have the balance, looks like it's a balanced equation, so see if you can figure that one out. And here's some heats of combustion. So these are the heats that you release when you burn these things. If you notice, octane, which is in gas, gives a lot of energy out compared to if you were just going to burn like graphite from your pencil. Remember, this has a lot of carbon and hydrogen bonding there. This just has the carbon. So that's why we use this in our cars, because it gives lots and lots of energy. We eat this sugar because it gives us tons of energy as well in our body. Heat of combustion is the heat of the reaction for the complete burning of 1 mole. So that's the definition of heat of combustion. And let's see how well what you learned out of this section. So I would recommend you pause this, read this. There's a lot of reading there. See if you can figure out the answer. Okay, I'm going to pause it. Go ahead and pause it, and now I'm going to give the answer. Okay, so enthalpy change of the reaction in the calorimeter. So you're going to have to pause this and figure out what's going on in this situation. When you see that reaction and then you see a negative sign for the kilojoules, what does that mean for the enthalpy? Okay, so negative means release, so exothermic. Okay, so this one you're probably going to have to pause me and use the formulas that we've used. Remember to do final minus initial on the temperature. So here's the answer. So see if you can get that one correct. And which of the following is a thermochemical equation for an endothermic reaction? So which would it be? So this one's showing the energy is needed on the beginning, the reactant side, so this is endothermic. So this is going to take you a while, so pause me, try to do this problem, and see how you do, and I'm going to give you the answer now. So see if you can come up with that answer there. Alright, so a lot for this section. I hope you learned a lot, and I'll talk to you soon. Bye-bye.